Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to be just an introductory video to Einstein's special theory of relativity and a concept called time dilation. So what I'd like you to do is pay attention to this part right here. Imagine we've got some car driving down the road, and maybe it's a convertible or something, and we got Nolan Ryan here. That's a baseball player from long ago. Nolan was famous for his 100-mile-an-hour fastball. Imagine that Nolan can throws that 100-mile-an-hour fastball, however, while the car is moving 60 miles per hour. This 100 miles per hour is with respect to a reference frame that Nolan Ryan is on, which is actually in the car. This 60 miles per hour is with respect to a reference frame on the Earth. So I'm going to go ahead and draw like a coordinate system here, x, y. That's a reference frame that young Timmy here is observing things happen. And as far as Timmy is concerned, if he put a radar on that ball, that radar would read 160 miles per hour. The velocity of that ball, as observed by Timmy, is going to be the velocity of the car plus the velocity with respect to the car. And in this case, that'll end up being 100 miles per hour. So this is an example of how velocities add in a relative sense. Hopefully there's nothing too crazy about that. Now what we're going to do here, though, is we're going to chat about, we're going to replace the ball with a flashlight. And our car here, we're going to imagine, can go quite a bit faster, not just 60 miles per hour, but what we're going to do is I'm going to express velocities in multiples of c, the speed of light. So if we imagine a light wave coming from the flashlight, right, that light is moving in this direction, velocity equal to c, the speed of light. This would be measured with respect to the car. Now let's imagine that the car is moving to the right at maybe 30% the speed of light. 0.3 c would be a good way to represent that. If we use the baseball analogy, if we think back to how the baseball velocity is added, we might conclude that the velocity of light with respect to Timmy would be 1.3 c. Well, it turns out that this just doesn't occur. And what Timmy would actually measure is c, the speed of light. So this is kind of what special relativity is about. And before I actually get to the time dilation part, I'm going to go over two what are called postulates of special relativity. All right, let me get rid of this stuff. We don't need this anymore. Okay, so postulate number one, that the laws of physics are the same in all non-accelerating frames of reference, or these are sometimes called inertial frames. So what that means, basically, if I've got a car, moving along, there's a reference frame that goes on that car. I could put a coordinate system x, y, and then maybe here's a reference frame attached to the Earth. Maybe I'll call that big X, big Y. As long as the car is not accelerating, all concepts of physics are equally valid in either reference frame. That's what that means. All right, postulate number two. The velocity of light is equal to c for all observers in any reference frame. So that should seem a little unnatural. What we're going to do now is assume that it does occur, and we're going to see what kind of consequences that have. All right, now, what I'm about to describe is Einstein's famous thought experiment about a person in a train. We're going to imagine Timmy here has that flashlight I was talking about, and we're going to imagine that the flashlight is pointing up. And imagine that there is a mirror up here that will reflect the light, the beam of light. Now, the train, we're going to imagine, is moving to the right with a velocity, let's call that v sub t for velocity of train. And what we're going to talk about now is how the light ray, as it goes up and reflects, comes back down, we're going to talk about how the time for it to do so for an observer on the train versus an observer here, Santa Claus, that's not on the train, how that time frame differs. So we're going to imagine the light beam. An observer on the train would observe that beam do this and back down again. If we were to attach some math to it, this is some height, let's just call it h. The total distance traveled would be 2h. Speed, I'm going to use is equal to distance, 2h, over time. And the speed here is going to be, the speed of light. We'll just say c. So this equation effectively represents the time observed by Timmy, the time it takes that light beam to go here and then back again. It's very easily solved for t, 2h over c, c being the speed of light. All right, now we're going to take a look at the problem as observed by Santa Claus here. Remember that this is occurring while the entire thing, oops, let me not do that, while the entire thing is moving to the right. So you got to imagine Santa Claus is observing this, that this is occurring in this fashion. So what Santa Claus would see is that light beam would follow this type of path, reflect off the mirror, come back down. Now, we're now going to calculate the time it takes for this to occur in Santa Claus's frame of reference. And I'm going to call that t prime. It's going to be a different t here. But we're going to use the same equations. Let's start with this. Distance is, speed is distance over time. The speed, however, we're going to use c, just like we did before, because of this postulate. All observers record a value of c for the speed of light. The distance we're going to use, though, is this distance from here and then to here. So we're going to have to do some geometry here. This distance is equal to the velocity of the train times t prime. And that makes this distance in green right here equal to half of that. And then this distance is h, the height. So I'm going to call this capital D here for this distance along the hypotenuse. Actually, let me go back and call that h for hypotenuse. The hypotenuse of that triangle squared is going to equal the height squared, that's this distance squared, plus this distance squared, which is half of this. So that's going to be plus velocity of the train times t prime squared. So the hypotenuse is equal to the square root of this. And the total distance traveled by the light beam is from here and then back again is 2 of those. So let's do this. Total distance traveled is equal to 2 times this, would be 2 times this guy. Now, speed of light, c, is going to equal the distance traveled, which is this, 2 times square root of h squared plus velocity of the train times t prime squared. Let's see, distance over time. Speed is distance over time. Okay, that's going to be t prime. So let's see, let's take this t prime and move it over here. So we're going to have t prime times c is equal to twice the square root of h squared plus velocity of the train times t prime squared. All right, now what we're going to do is we're going to kind of put these equations together here. You notice there's an h here, and I'm going to go back to Timmy's frame of reference. We can get the h from this equation right here. The h is going to equal t times c over 2. And again, where this t was the time frame measured by Timmy. So now we're going to have t prime times c is equal to 2 times the square root of h, let's see, which is t c over 2 squared plus this term squared, velocity of the train times t prime squared. And now we're finally getting somewhere that's starting to get really interesting. Let me get rid of some of this stuff so we can talk about that equation here. Need some more room. All right, so let's take a look at this. First of all, you'll notice that we have an equation and it's got t's and t primes in it. And that's starting to suggest here, ooh, these things might be, they might look a little bit different. Let's start kind of unwinding this. If I put the 2 over to the left and then we square both sides, what we're going to have is t prime times c over 2 squared is equal to, now when we square this on the right, this radical will be gone, tc over 2 squared plus velocity of the train times t prime squared. And what we're going to do now is solve for t prime in terms of t. Let's move this term to the left and factor out the t prime. Let's see, what are we going to have here? C squared over 4 minus velocity of the train times, whoops, squared, moving this over to the left. Oops, and then we're going to have to factor. Let's do that. That's squared equals t times c squared over 4. I think I've done that algebra right. I'm going to stare at that a little bit further. T prime c squared over 4, t prime c squared over 4. Subtract this, and that's the velocity of the train squared. Factor out the t prime. I think we're good. All right. Now what we're going to do here is let's take this and let's multiply everything by 4 over c squared. So then we're going to have t prime squared times the quantity. Now, when we multiply this by 4 over c squared, that is going to be a 1 minus. Now, when we multiply this by 4 over c squared, let's see, that's going to be a v, velocity of the train, squared over c squared, and then we're going to have a 4 there. I'm going to take a moment, pause this, and think about that 4, because I wasn't expecting that. I may have to go back and look for a little bit of a glitch. Pardon me. Okay, I'm back here, and I have to apologize here because I did make a little algebra goof. Probably have to redo this video, but for now I'm just going to go ahead and post it. If I go back here, this term right here was coming from this green distance, and it's not velocity train times t prime, it's half of that. So I forgot a 2 right here. My apologies for that. That's going to put a 2 here, here. Squared would be a 4 here. Then when we multiply both sides now by c squared over 4, this would be gone. So what we have now is that we have this relationship. Let's see. Again, taking this, and I think what I'll do is remultiply that. Let me get rid of that. I will redo this video later, so that's a little smoother. But if we take this thing now and we multiply by 4 over c squared, all the 4's are gone. And we've got that t prime squared times 1 minus v squared over c squared, where that v is the velocity of the train. I'm going to leave the t off it for now, is equal to t. Oh, t squared. And then if we square root both sides, here we finally get to the action here. We've got t prime times the square root of 1 minus v squared over c squared is equal to t. So this is the really important result. Sorry that was kind of a long-winded way to get there, and the algebra was a little goofed up. That's the big ticket thing right there. So I think what I'll do is get rid of all this other stuff we do not need. Chat about that thing all by itself. All right. This equation here is saying that there is a difference in the time that is observed. Even though these two people are observing exactly the same event, the light ray to go from here and back down again, Santa Claus sees the light going from here to here, but this is again exactly the same event. Their perceived times are different, and they differ by this factor. If you'll notice this thing right here is less than 1 because it's 1 minus something. Right? This something is usually very, very, very small. If this train is moving at like 20 miles per hour, 20 mile per hour over the speed of light is practically 0. And then the time that Timmy observes is the same as the time that Santa observes, or basically the same. However, when the velocity starts approaching c, so imagine it's something like 30% the speed of light, 0.3 c, and I run that equation, this is now going to read t prime times the square root of 1 minus, now if you put a 0.3 c here and square it, we're just going to have 0.3 squared. And I'm going to go ahead and calculate a value here. If you give me a moment, I've got to find a calculator. Okay, so now what we have is that t prime times 0.954 is equal to t. So you see that there's an actual reasonable measurable difference here. You know, if, for example, in Timmy's time frame, say we measure something that's maybe, I don't know, 100 minutes, then t prime, and again I'm doing this example for t equals 100 minutes, just picking something off the top of my head, then t prime would be 100 divided by 0.954. 105 minutes, basically, approximately 105 minutes. So you'll notice that, you know, we have this difference now between the time values measured between Timmy and Santa Claus here. And you notice that Timmy's time frame is slowed down relative to Santa Claus. And the faster and faster Timmy goes, like if this were to approach 0.6c, 0.7c, 0.9c, the more pronounced these time differences will be. I'm going to save an example here. I'm going to go ahead and save another example for another video because I see this thing's getting 16 minutes. But this effect is called time dilation. It has been proven time and time again, you know, lots of different ways. One way it's been proven is people take what are called atomic clocks, which are extraordinarily accurate, and you take two of them that are reading perfectly the same, and then you leave one on the ground and you fly one in an airplane for a while, or a jet, and when that jet lands and you compare the clocks, you know, the clock on the ground might say this much time has went by, but the clock in the air will say like only, you know, a smaller amount of time has went by. These clocks will no longer be synchronized. So again, that effect is called time dilation, and this is just part of Einstein's special theory of relativity. All right, I hope that helps demonstrate the theory. Have a great day.